Hi, welcome to this lesson on Euclidean geometry, the Pythagorean theorem. Let's have a look at question 3. In triangle PQR, we are given that RQ is perpendicular to QP. Okay, so it's a right angle triangle. And QT is perpendicular to RP. Okay, so this red line here. We are given that PQ is 2 centimeters. QR, so this length here, is B centimeters. RT, which is this length here, is 3 centimeters, and the length of TP is A centimeters. Okay, so off the bat, I can see 3 right angle triangles that are coming out there, so I'm just going to extract them out rather, and then label them. So there's PQR, that's B units. It's going to be 3 plus the A, so this is going to be 3 plus A units long for the hypotenuse, and 2 units here. Then there are 2 more right angle triangles in this diagram. Okay, so there's this triangle here, which is RQT, right, where RT is 3 centimeters. QT, we don't know the length, and RQ is B units. Okay, and then lastly, this right angle triangle, QTP, that's A units, 2 units for the hypotenuse, and QT we don't know the length of. Okay, so they want us to work out A and B giving reasons. So now we have 3 right angle triangles where we know 2 lengths here and an unknown length here, and we know 2 lengths here and an unknown length here, and we know all 3 lengths in this bigger triangle RQP. So if we use the Pythagorean theorem in all 3 of these triangles, we're going to get equations that have A's and B's in them. So this problem in geometry now turns into a problem in algebra, where we're going to analyze simultaneous equations and then solve for A and B. Okay, so let's analyze each triangle. So I'm going to say in the bigger triangle, so in triangle PQR, we have the following. So the hypotenuse is RP. So I'm going to have B squared plus 2 squared equals 3 plus A all squared. Okay? So if I simplify this algebraically, on the left-hand side, 2 squared is 4, B squared is just B squared, and then on the right-hand side, if I square that binomial out, okay, A squared, then 3 times A is 3A, double that product, that gives us 6A, and then 3 squared is 9. Okay? So we've got one equation so far. I'm going to leave it like that for now, and I'm not going to simplify just yet. Okay, and then look at all the other triangles. Okay, so in triangle RQT, so this one here now, I can use the Pythagorean theorem again because of that right angle. So I have the length QT all squared plus RT, which is 3 squared, equals B squared. Okay, so this implies then that 9 plus QT all squared equals B squared. Okay, so I'm going to call that equation 1 for now up here and equation 2 over here. Okay, and then in the last triangle, triangle QTP, okay, because it's a 90-degree angle again, I can use the Pythagorean theorem. So it's going to be QT all squared plus A squared equals 2 squared. Okay, so simplifying that, A squared is just A squared, QT squared is QT squared, and then 2 squared is 4. So I'm going to call this equation 3. Okay, notice that there's 2 equations with QT. All right, so what I'm going to do is I'm going to subtract equation 2 from equation 3 as follows. So on the left-hand side, the QT squares will cancel, so I'm left with 9 minus A squared. And on the right-hand side, I'm left with B squared minus 4. Okay, so I'm going to call this equation 4 that I've generated. So now look here, I have in equation 1 an equation with A squareds, A's, and B's, and on equation 4 I have an equation with A squareds and B squareds. Okay, so I think let's try and simplify the problem by looking at equation 4 and making B squared the subject of the equation, because then I can replace B squared here, and then hopefully it'll just be all in terms of A's, and then we can solve. Okay, so b squared minus 4, so I need to add 4 to both sides. So I'm going to get 9 plus 4, that's 13, minus a squared. Okay, so now I'm going to substitute this value into equation 1. Okay, so you can see how we're using simultaneous equations here now. Okay, so in equation 1, 4 plus b squared, but b squared is 13 minus a squared, equals a squared plus 6a plus 9. Okay, so now I can solve. So on the left-hand side, 4 plus 13 is 17 minus a squared equals a squared plus 6a plus 9. Okay, so now I'm going to bring all the terms on the left-hand side to the right. So if I add a squared to both sides, I'm going to have 2a squared plus 6a. And then I need to subtract 17 on both sides. So what's 9 minus 17? I think that's going to give you negative 8. That's equal to 0. So now we have a quadratic equation in the variable a that we can solve for. Next is a common factor of 2, so I can divide everything by 2, and I'll get a squared plus 3a minus 6 equals 0. Okay. Alright, so we're carrying on with the equation here, just making sure that everything we've done algebraically so far is sound. Okay, so now I need to solve for a here. Alright, so can this be easily factorizable? Well, the factors of 6 are 1 and 6 and 3 and 2. So I don't think any one of those combinations is going to give us a 3a in the middle there. Okay, so I'm going to, I think I might have just found my mistake. Okay, very easy to make these arithmetic mistakes. Alright, when I had on the left-hand side was a minus 8 here, alright, but dividing by 2, that should not be minus 6 there, okay? Negative 8 divided by 2 is negative 4. That is more easily factorizable, right? Because now the factors of 4 that make up a difference of 3 are 1 and 4. So I can say I want more positive 3a, so I'm going to say a plus 4 times a minus 1. Alright, so now that gives me two options for a. A could be negative 4 or a could equal 1. Now let's think about the context of the question here. A represents a length in this triangle, so it does not make sense for a to be a negative number. So a must equal 1, and therefore I can substitute that back into this equation here that I had in equation 4 and find that b squared equals 13 minus 1 squared. So 13 minus 1 squared is 13 minus 1, which is 12. So therefore b now is going to be the square root of 12, but I'm going to take the positive square root of 12 and not the negative, because again b is a length. Okay, so my solution here is that a is going to be 1 centimeter and b is going to be root 12 centimeters. And you can simplify root 12 if you want. That's 4 times 3. That's going to be root 4 times root 3, which is 2 root 3 centimeters. Okay, so those are two lengths. And again, if we test it in each right angle triangle, we'll see that the Pythagorean theorem is satisfied for all three triangles. All right, so that's how we would do this type of question. I'll see you in the next one.